Today we're beginning our first look at motors, but before I get to that, let's cover some additional information about rotating mechanical systems. If you took my class last term, this will be review. Kinetic energy of a flywheel is given by this equation, 1/2 I omega squared, where I is the moment of inertia and omega is the angular velocity in radians per second. So remember that I is dependent on two things. It depends on mass of the object and it depends on the distribution of that mass. Around the axis of rotation. So if two flywheels weigh the same amount or have the same mass, but that mass is distributed differently or they have different shapes, then they will have different moments of inertia. So it's not just the mass that counts, it's also the shape of the object, the distribution of the mass. So I'm going to give you two examples. If we have a solid cylinder, and in this case the shape looks something like this. Now the important thing is that we could spin this shape around multiple axes. So I'm going to give you the moment of inertia if the axis is positioned like this. If so, then I is equal to 1/2 of the mass times the radius squared. So the cylinder has some radius, some total mass. Plug those into this formula and you have the moment of inertia. If we have a solid sphere, then I is equal to 2/5 mr squared. And here I don't need to define an axis of rotation because for a sphere, as long as we're passing through the center, they're all equivalent. So that's some refresher on flywheels. Rotational kinetic energy is given by this formula. And a couple of shapes, I've given you the moment of inertia. Every shape has its own special formula for moment of inertia. Now I want to introduce you to some additional power units. So far we've talked about, in the English system, foot-pounds per second. And in the metric system, we've talked about watts. So there's an additional unit which is very handy to use in the English system. It's called the horsepower, and I abbreviate it HP. And in the metric system, more commonly we talk about kilowatts, because a watt is a fairly small unit. Kilowatts is more comfortable to deal with motors. Same thing for horsepower. It's much larger than a foot-pound per second. So it's just a more convenient unit to use when we discuss motors. So let me give you some conversion factors. 1 horsepower is about equal to 550 foot-pounds per second. And 1 horsepower is also equal to 0.746 kilowatts. So we can get horsepower both from the English unit, foot-pounds per second, and also from kilowatts. This one here is especially important to know because oftentimes we're going to be dealing with a motor that's rated in horsepower, but we need to know the energy usage of that motor. And the easiest way to do that is to convert it to kilowatts after accounting for efficiency and then multiply by the number of hours. So this one's probably something you should memorize. We also, as we introduce new units, we have to change the equations that we use to calculate certain things. So I'm going to introduce a term called working equations. So easiest way to describe that is with an example. So let's say I've got power equation. Power is equal to force times velocity. This is for linear motion. So the force applied to an object times its velocity gives us the power. Now if I want that power to be expressed in horsepower, I could calculate this out in English units. So if I have force is measured in pounds and velocity is measured in feet per second, if I were to just plug those numbers in for this, I would get power in foot-pounds per second. So if I want my power instead to be in horsepower, I need to do a unit conversion. So I would just divide this by 550 based on the conversion I gave you on the previous slide. So I plug in my force in pounds, velocity in feet per second, divide by 550. That gives me my power in horsepower. So this equation right here is what we call a working equation. It's got variables, but it's also got a collection of conversion factors in terms of a single constant typically. So let me give you another example for rotational power. So here we've got power is equal to torque times angular velocity. Torque is measured in pound-feet, and angular velocity, in this standard equation, angular velocity is measured in radians per second, and it would give us power in foot-pounds per second. But if I want power to be in horsepower, it's usually more convenient to talk about angular velocity in terms of RPM, revolutions per minute. So if I have torque in pound-feet, omega is in RPMs, and power is in horsepower, I can do that by dividing this equation by 52. So I plug those in, divide by 5252. That gives me my power in horsepower. So as we go through the term, we're going to see several working equations like this where the units that these variables are in are specified ahead of time. And then we have some constant that gives us some desired power unit or some desired energy unit. So it's a good idea to start collecting all these equations on some reference paper that you can keep with you. Okay, now let's get to motors. So in general, a motor is a device that converts electrical energy to mechanical. And in general, it's rotational mechanical. So that is a motor. Opposite of a motor is known as a generator. Convert mechanical, again, typically rotational, into electrical energy. So motors are one of the most important machines that we study because of their applications for HVAC systems. Almost all HVAC systems use a motor of some sort to move energy throughout the building. So we need to develop a pretty good understanding of how motors work. So first let's talk about efficiency. As we learned last term, anytime you have an energy conversion from one type to another, you have losses due to friction or other physical forces at work. So if I have an electrical energy to a mechanical energy conversion, then I have some losses. And those losses are quantified using the efficiency number. And remember, we abbreviate efficiency with Greek letter eta. And as I mentioned in the notes, the motor efficiency varies through a lot of different factors. We could talk about quality of construction. So you can buy motors that are premium motors. They'll typically have a higher efficiency rating than the standard construction. Type of motor in terms of whether it's a three-phase motor or single phase. And don't worry about the distinctions between these for now. We're going to discuss that in a later lecture. Motor size. Typically, larger motors are more efficient than smaller motors. We have motor load. For most motors, when they're running at full load or full power output, they are at their most efficient. As you decrease the load, so the motor isn't working as hard, the efficiency drops. And in the notes, I provided you with a table that gives standard efficiency numbers for various horsepower size of motors from 1 to 100. And you can see there's a standard and a premium efficiency. So you should check the notes for that. Just be aware that typically there's an extra cost associated with a premium efficiency motor. So one of the things you can look at is, okay, if the premium efficiency motor costs more to start with, how much money does it save me over the lifetime of the motor in terms of energy costs? So I think you'll find that depending on the type of motor, a lot of times it's worth it to go with the premium efficiency motor. Even though it costs you more initially, you can save money in the long run. That's the type of thing we will study quantitatively in the fall with energy investment analysis. Okay, next we look at motor speed. So motors essentially have these rotating magnets inside of them, and as you pass electrical current around coiled wire around the magnets, it causes the motor to turn. So we can measure how fast that occurs. That's the speed of the motor. And the speed varies on a couple of things. It varies on what's called the number of poles. And that simply has to do with the number of pairs of magnetic poles that constitute the rotor of the motor. You don't have to worry about that too much. Just know that different motors have different construction types, and they have different numbers of poles. Speed also varies based on how hard the motor is working or the load. So if the load is very low, the motor is not working very hard, the speed increases. If the motor is at full load, the speed decreases. Now there's a special type of speed that we look at, which is called synchronous speed. And this is equivalent to the speed of the motor under no load or zero load. So if the motor is just spinning, but there's nothing attached to it, it's not doing any work, it's spinning at some speed which we call the synchronous speed. The actual value that this takes on depends on, again, the number of poles and also the frequency. And by frequency, I'm talking about the electrical frequency. So in the United States, we have 60 hertz power for AC motors. Hertz is abbreviated capital H, lowercase z. It just means how many cycles per second for alternating current. 60 hertz for the US, typically 50 hertz in Europe. So at this frequency, and given the number of poles, we can figure out what the synchronous speed of a motor is. So I'll give you some examples which are detailed in the notes, but if I have 2 poles, so this is my number of poles, and this is my synchronous speed. 2 poles gives me 3,600 RPM. 4 poles, I have half that, 1,800 RPM. And then all the way down to, I've given you a table in the notes, all the way down to 10 poles would be 720. RPM. Another concept that is related to speed is called slip. Slip is basically the difference between the RPMs at synchronous speed minus the RPM that the motor is operating. So let's do an example. If I have a 2-pole motor, my synchronous speed is 3600, and let's say that at some particular load my motor is spinning at 3500 RPM. So I can tell right away that my motor is not at zero load because it's spinning at a speed lower than the synchronous speed. Synchronous speed, remember, is the speed under no load. So if I have some load and speed decreases with increasing load, then that's my operating point. So if I subtract these two numbers, I get a slip of 100. That's just an example again. A very important thing to remember about motor speed is that speed is inversely related to my power output. So the higher the speed, lower the power output. Greater the speed, lower the speed, higher the power output. So depending on the type of motor, you can have maximum power output or maximum torque at 0 RPM or whatever the lowest speed is. And similarly, when it's at the highest speed, you have the lowest power output. And that kind of makes sense if you think about this speed under no load. If it's under no load, it's outputting very little power, very close to 0 power. So that's the maximum speed that the motor will run at. Okay, next I want to show you an example of a motor nameplate. And this is something that's very important to look for when you're looking at HVAC systems. You'll often see motors on pumps or motors on fans, and they typically have some kind of identifying label, sometimes paper, sometimes metal, but it's attached right to the motor, and it gives you a lot of good information about the motor that you can use to do some energy calculations. So I want to show you that motor nameplate, and this is an example of it. You can see in this example, one of the most important things to look for is the horsepower. That's right here. So this motor has a 1 horsepower. We can see the voltage. So this motor can be run on 460 volts or from 208 to 230. And depending on which voltage it uses, so that's the voltage, depending on what voltage it uses determines the current. So for example, if it's 208 volts, it's going to take 3.8 amps. At 230 volts, it'll take 3.6, and at 460, it'll take 1.8. So voltage is measured in volts. Current is measured in amps. And I should tell you that these are the full load amps. So when the motor is working as hard as it was designed to, that's how much current it will draw. Another important thing to look for is the efficiency. So here it's telling you that at full load, the efficiency of this motor is 77%, which is not very good. So efficiency. That's given in some percentage. NEMA stands for National Electrical Manufacturers Association. So they are the ones that do certifications for motors like this. Let's see, we can see that the phase is a 3-phase motor. It's given here. So we also look at the phase. We can see the speed should be on here somewhere. There it is. 1720. That's the speed when the motor is at full load. So phase is typically 1 or 3. And I circled it, but just mention again power in horsepower. So for motors in the United States, you have power and horsepower, speed and RPM, phase 1 or 3, voltage in volts, current in amps, and efficiency. These are all full load characteristics, and these are the 6 most important things to get off the nameplate other than the model number itself. Sometimes some of this information may be missing, so if you can grab the model number and look it up by manufacturer, sometimes they have catalogs online, other types of manufacturing data online. It's all useful stuff to look up. Okay, another important characteristic of a motor is what's known as the load factor, abbreviated LF. Load factor. This is basically a percentage that measures how hard the motor is working compared to its full output. So if my load factor is 100%, then my motor is working at full load. So basically, load factor in terms of an equation is my power output at at partial load, PL, divided by my power output at full load. So if I have a 3 horsepower motor and it's working at 1.5 horsepower at partial load, my load factor would be 50%. So let me write down an example. My motor is a 3 horsepower and it's working at 1.5 horsepower. My load factor is 1.5 over 3, or 50%, or 0.5. So load factor comes into play when we look at HVAC systems a lot, because most of the time an HVAC motor is not operating at full load. It's operating at some point lower than full load. And if it's operating too low, that's an energy conservation measure, because if we can replace that motor with a lower horsepower motor, which means it'll be higher efficiency, because remember, the higher the load factor, the higher the efficiency of the motor. The harder it's working, or the harder it is working close to its full load, the more efficient it is. And as a general rule of thumb, again, this is manufacturer specific and depends on a lot of other things, but if we're over 50% load factor, then the efficiency stays pretty close to the full load efficiency, especially for large motors. But under 50%, you're going to notice larger drop-offs in efficiency. So if your motor is not working very hard at all, under 50% of what it could do, that's when you would investigate possibly replacing that motor. And you're going to see this drop-off in efficiency. It's going to be more dramatic for smaller sized motors, like under 1 horsepower. So I've given you one formula here for load factor, but there's another one we need to know, which has to do with the slip. So I'm going to abbreviate that slip as S, slip at partial load, divided by the slip at full load. So let's do an example. Let's say I have a 2-pole motor. Therefore, my synchronous speed is equal to 3,600 RPM. Let's say my full load speed is 35, let's say it's 3,400. and let's say my part load speed is 3,500. We want to know what is the load factor of that motor at that operating point. So my load factor is equal to the slip at part load. So remember, slip is synchronous speed minus the part load speed. So that'd be 3,600 minus 3,500. My slip at full load is equal to synchronous speed minus my full load speed, which is 3,400. That gives me 100 divided by 200, or 50%. So under these conditions, this type of motor is at half load. So this relationship is important to write down because it gives us a way to have a correspondence between the power output of the motor and the speed.